Unit 5, Calculus, Day 41 Notes, Part 2. And we're applying different theorems in calculus. Intermediate value theorem, IVT, extreme value theorem, EVT, Rolle's theorem, and mean value theorem, MVT. So we have a problem here. The rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. The table below shows the rate as measured every 3 hours for a 24-hour period. So again, we have water flowing out, and they talk about it in gallons per hour. So that's going to be some sort of rate. So the question asks, estimate the value, again, estimate the value of the derivative of this function r when time equals 5, indicating correct units of measure. Explain what this value means about r of t. Well, 5 is going to fall somewhere in between 3 and 6. Again, I don't know what the function r is, but I know, again, as I look from 3 to 6, I know I can use the mean value theorem. It depends what it is, that the secant line right there is somehow going to be an estimation for this tangent at when x equals 5. So let's take a look at that. So, hey, the derivative of that function, x equals 5, is going to be approximately equal to, it's an estimation, when I look at r of 3 minus r of 6 all over 3 minus 6. Well, hey, do I know r of 3? Yeah, 10.4. So 10.4 minus r of 6 is 10.8. All over 3 minus 6 is going to be negative 3. And what do I get up here? I get negative zero point 0.4. Take my calculator, and we're going to get roughly um, 0.133. And again, it's gallons per hour is what this RFT was all over T. So it's gallons per hour all over gallons per hour. But it's also per hour. So that's going to be gallons per hour squared. Okay, so what the heck does that mean? It tells me that since, let me put this in a different color here, since the derivative is greater than 0, then I know the rate at which the water is flowing out of the pipe is now going to be increasing at x equals 5. And again, we can see gallons per hour here, 10.4, 10.8. And this is an estimation of the instantaneous rate of change, looking at the average rate of change. Okay, and again, it looks like it's increasing, increasing, that starts to decrease, 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 decrease. But at that instant, we're estimating that it's going to be increasing. Again, what we said, the rate at which water is flowing out of the pipe is going to be increasing at time equals 5. And that's what r prime 5 is, the derivative at 5. That's an approximation using the mean value theorem, allows us to use what we know about the average rate of change and saying that, hey, at least at one point it would have to be equal to. So that's what we're looking at here. Now I want to kind of do the same thing on B, but they actually ask us to find the average rate of change. So using correct measures of units, once again, let's find the average rate of change of R of t from time equals 13, time equals 3 to time equals 18. So now we're going to average rate of change. We're thinking secant line, which is just a slope formula, rate of change, and slope formula is going to be change in y all over change in x. Um, R, R3 is 10.4 minus 10.7 all over 3 minus 18. We had two negative values, so I know it's going to be positive, but I'll write it as negative. Negative 0.3 all over 15, and take the calculator, and it's going to be equal to it's going to be 1 over 50, which is going to be 0.02. And once again, the correct units of measure, the R3 over R8, R3 minus R18 is gallons per hour, and it's gallons per hour over hour, which is gallons per hour squared. Okay, the last one here. Is there some time t between 0 and 24, so using the whole chart, such that the derivative, or the slope of the tangent line, has to equal 0? Justify your answer. Well, again, Rolle's theorem says, hey, I can guarantee that there's going to be um, there's going to be a value where the tangent is equal to slope of the tangent line equals 0. First, it has to be differentiable, and next it has to be continuous, which the water's always coming out, and then these values must be equal. And since that's true, then the Rolle's theorem guarantees that I'm going to get some slope of a tangent line that equals 0. So let me write that out. Okay, so just take a second. That's what we just said. So since the function is differentiable on the closed interval from 0 to 24, and the value of the function at the endpoints both equal 9.6, then Rolle's theorem guarantees a value of t on that open interval 0 to 24 such that the slope of the tangent line, or the derivative, equals 0. Okay, that'll be it for part 2.